Welcome to week 3. We're going to be transitioning from our discussion of vector calculus to focusing on electrostatics. We're still going to get to surface integrals and line integrals, but we're going to cover them when we need them, and we need surface integrals for electrostatics. But today I really want to make sure you have a solid conceptual foundation before we go back into doing all the calculations. To start with, we're going to talk about what electrostatics means. Electrostatics primarily deals with calculating the electric field or the electric potential when you have static charges. So you have electric charges, but they are not moving. So which of Maxwell's equations apply to this situation? I'm going to go ahead and remind you of Maxwell's equations. So this first equation about the divergence of E does matter because this rho is an electric charge density. So what this one tells us is that when there's an electric charge density, that's going to create an electric field with divergence. And now that you've been working with divergence and curl a little bit more, I hope when you read this, it has more meaning to you. Okay, let's come over to this one. This one says that the divergence of the magnetic field is always 0. This is a consequence of there being no magnetic monopoles, and we'll come back to thinking about that later in the semester when we're looking at magnetostatics. Okay, what about this other magnetic field one? J is a current, and when we're talking about static charges, there's no current. So a current produces curl and magnetic field, and a changing electric field produces curl and magnetic field. Well, the electric field we're creating over here isn't going to be changing in time because our charges aren't moving. So there's nothing coming from here either. So that means that there's no magnetic field with curl, there's no magnetic field with divergence, so we don't really need either of these right now. This one says an electric field with curl is created when there's a magnetic field that changes in time. Well, we just said there's no magnetic field right now. So this one doesn't apply right now either. So the only one we really need is this one. That the divergence of the electric field is created by electric charge density. Now the fact that we're dealing with electric fields that don't have any curl is actually very important when it comes to talking about potential. It's true for gravitational fields in addition to electric fields, that in order to have potential energy, you can't have any curl in your fields. Okay, so we have one equation to work with. How can we use it? Well, typically what we want to do is that we'll know where our electric charges are, and we want to figure out the electric field. So this form of the equation you can use if you know the electric field, you can calculate the divergence of it. That'll give you the electric charge density. But very rarely is that a situation that you're in. So we're going to focus on the other direction. So to make this into something usable, we're going to do a volume integral on both sides of this equation. So I'm going to copy it down. I'm going to write little v's at the bottom of the integral to indicate that I'm doing a volume integral rather than writing out 3 integral symbols. The d tau is an infinitesimal volume element, so you just have a little cube if you're in Cartesian coordinates. So in Cartesian coordinates, right, that'd be dx, dy, dz, and we have our different combinations depending on which coordinate system we're in. So we're just writing d tau, so what we're doing right now doesn't depend on what coordinate system we're in. Okay, so we have 2 volume integrals. What can we do with these? Well, the right side, I think after last week, should look familiar. I'm just going to pull out the constant. So you should recognize this as total charge because it's an electric charge density integrated over a volume. So I'm going to call that Q total for now. But what are we supposed to do with integrating the divergence of the electric field when we don't know what the electric field is? Well, there's a trick we need to use. It's called the divergence theorem. It actually has a couple different names, but we'll just go with the divergence theorem for now. Okay, so what the divergence theorem says is if you have a vector field, you have the divergence of the vector field integrated over a volume. It says that this calculation will give you the same result as if you took a closed surface and you integrated a surface integral of that field over that closed surface. Now this actually makes the most conceptual sense in E&M to me. So let's make sure you understand what all these symbols mean. So we already talked about the left side. On the right side, that circle right there that's on the integral means it's for a closed surface. That S, I'm just writing to remind you this is a surface integral, and dA is what you do for a surface integral. So say if you were integrating over the xy plane, dA would be something like dx dy, or if you're doing it over the yz plane, it'd be dy dz. And there are different combinations when you're in spherical or cylindrical coordinates. So let's just talk a little bit more about what I mean by closed surface so we can understand what that means. So an open surface could just be, these are 3D drawings. Say you have a square. You could do an integral of a vector field over a square. But a closed surface would be a cube. Right, because it's a closed object. Or an open surface could be a circle. But a closed surface would be a sphere. Alright, I hope that makes sense. So this means we can make a substitution into what we had on the previous page. So let's write out what we get. So instead of the divergence of the electric field, we're going to have a surface integral over the electric field. And don't worry, we're going to talk more about what this surface integral means. I want to make sure you have a really understanding what surface integrals mean before I ask you to actually calculate any of them. Okay, so this is what we get when we use the divergence theorem to write down that integral we had before. So now this says that if we do the surface integral of the electric field over a closed surface, that will equal 1 over this constant, epsilon naught is a fundamental constant, times the total charge enclosed inside of that surface. So say if we were talking about, say we had a sphere with some charge density in it. This says that the electric flux through the surface of the sphere is proportional to the charge within this sphere. This is Gauss's law. So I've been referring to the surface integral, but we haven't really worked with it much yet. So we're going to really look at this integral in detail. So we looked at the volume integral last week. Now we're going to focus on how we do that integral. So what's this mean? I'm going to talk about this a little bit more generally and say, all right, what if we just have the electric flux, just a surface integral of an electric field? So the electric flux is the surface integral of the electric field. I'm not sure in which AP Physics classes you do much with this. You may have seen it if you just deal with like the electric field through a square or a circle. You might have seen it as E dot A, or you might write as EA cosine theta. And again, I'm not sure what it looks like in APB or APC physics, or I guess APB is now AP1 and 2, and I definitely don't know what it looks like in AP1 and 2. So you'll have to tell me what you have done with electric flux so far. I'm really interested to know what your background is, but we're going to go through this step by step. So if you have seen it where you just have E times A, that'll work as long as the electric field doesn't vary over the surface, and we're not even going to do anything where that's not the case today actually. Okay, so let's back up a bit and just think about what the electric field looks like for some real physical situations. Now, I know a lot of you have been saying that thinking about how to draw vector fields is hard for you. And yes, it is hard to do. It takes a lot of practice. But I think a lot of you are like me in that once you see it in a real physical situation, it will make a lot more sense. So we're going to be thinking about what electric fields should look like for various charge distributions. An important thing to remember is if you're accustomed to drawing field lines rather than vector fields, the arrows in the vector fields always run tangent to electric field lines. So it does have connection to something you already know. So let's say we just have a positive point charge. And we're not even going to worry about drawing coordinate axes right now. So I have my positive point charge right here. So then we have our electric field pointing away from it because it's a positive charge. Electric field lines, well, electric field vectors point away from positive charges and toward negative charges. And these arrows should get smaller as we get further away from the charge. Okay, so just using the rule that your arrow should point away from positive charges and towards negative charges, and thinking about what you do know about electric field lines, I'm going to give you a couple situations so you can have a go at thinking about what the electric field vectors should look like in a couple of situations. And after you have a few minutes to think about it, then I will go ahead and show you. But I bet a lot of you will get it right on your first guess. Okay, so go ahead and draw the electric field for these three different situations. The first one where you just have a negative point charge, the second one where you have a positive point charge and a negative point charge and they're near each other, and the third one where you have a sheet of positive charge. All right, pause the video and try it out. So for a negative point charge, all the arrows need to be pointing towards that point charge and they need to be smaller as they get further away. So it looks pretty similar to the positive point charge, just going the other way. So in my drawing, I have the positive point charge on the left and the negative point charge on the right. So near the positive point charge, all the arrows are pointing away from the charge. Near the negative point charge, all the arrows are pointing towards the charge. And then you kind of have this curvy connection here that you may be more accustomed to thinking about when you're looking at, say, a bar magnet. It is very similar to looking at a bar magnet. Okay, but notice I made the arrows smaller between the two. And whenever you sketch these things, remember they don't need to be perfect, they just need to give you a general idea. Okay, last one. Okay, so when you have a sheet of positive charge, here I've drawn it from the edge on view, so you have positive charges all in a line, and all our electric field vectors then need to point away from the positive charges. Now, I don't know if these arrows are going to stay the same size as we get further away, or if they're going to get smaller as we get farther away. Gauss's law can help us figure that out, and we'll get there. Okay, so now we've thought about what our electric field vectors should look like. Now let's talk about defining the surface. That's the next step we need to use Gauss's law and to calculate electric flux in general. So we've looked at the E, now we need to look at the dA. So what does dA mean? So say you have this surface, it's a square. What dA is an infinitesimally small area on the surface. It's defined by, as I mentioned, in xy coordinates, it would be dx dy, but it needs a direction. That's n hat. Whatever direction n hat is, is perpendicular to the surface. So in this case, if this is dx dy, n hat is z hat. Now it could be in the positive z hat direction or in the negative z hat direction. When it's an open surface, either one is valid. However, when you're doing a closed surface integral, which is what we do in Gauss's law, n hat, the direction of your surface vector, always needs to point outwards, not inwards. So d is a vector that points outwards. This cube has 6 sides, so it has 6 different dAs. So now to help you practice this, I'm going to give you a couple examples to do yourself. So I'm going to give you some surfaces, and I'm going to ask you to draw which direction dA is going on that surface, just like I did for this cube. And if it's a 3-dimensional surface, remember you may need multiple dAs. Just like for that cube, you need 6 dAs. So this first one is a flat disk. This second one is a sphere. And this third one is a cylinder. So go ahead and try to draw dA for each one of these surfaces. For this flat disk, dA could either go up or go down. This is an open surface, so either one is correct. For the sphere, dA just needs to be radially outwards. All of these are defined by the same vector direction. They're all in the r hat direction. But depending on where you are on a sphere, it points in a different direction. That's the funny nature of spherical coordinates. All right, last one. For the cylinder, you need a couple different dAs. So this dA is in the z hat direction. This dA is in the minus z hat direction. Both of these two dAs I drew on the side are actually the same dA. I just drew them at a couple different points. Those two are in the s hat direction. All right. We're going to be using cylindrical and spherical coordinates a lot when we get into using Gauss's law when we're doing the calculations. Okay, so now we've looked at the electric field, we've looked at dA. Let's put them together. Okay, so when we're calculating the flux, we're taking a surface integral. You should notice in the surface integral, it's the dot product E dot dA. So you have the electric field at some point represented by the vector, and then you have some surface that has a dA. In this case, I'm trying to draw in 3D. It makes sense to me. Let me know if it doesn't make sense to you. Okay, so in this case, dA is also going in this direction. So when E and dA are going in the same direction, that gives you an electric flux with its maximum positive value. And again, if you're in a situation where the electric field doesn't actually vary over the surface, you can just do E dot A, where the direction of A is the same direction you would define dA to be. And that also means that you have EA. Cosine theta is another way of writing this. And this is the way most high school classes that I'm aware of teach anything that has a dot product. You don't tell the students you're doing a dot product, you tell them they're doing trig. And that's the same thing that I do in my intro physics classes. So this theta is the angle between the area vector and the electric field vector. And it's inside the integral because this can vary with position if we're going to be absolutely general. But let's stick to the simple case. We'll just do a simple example. Say we have a uniform electric field. So say it's between two plates. So you just have a constant electric field and you have a surface that looks like this. Now if I define dA to be up, then this will give us our maximum positive flux. If I had defined dA to be in the opposite direction, I would have gotten a maximum negative flux. Or let's say our electric field is going this way again. Let's say our surface is actually parallel to your arrows, which means that your dA is perpendicular to your electric field. Well, here you have zero flux. You should think about when you're thinking about flux is the density of arrows passing through the surface. So when the surface is parallel, the arrows aren't passing through the surface, so the flux is zero. Whereas when the arrows are perpendicular to the surface, all those arrows are going through. But if your arrows were at an angle, you'd have some non-zero flux, but only the perpendicular components of those arrows are counting. And I know we do this sort of thing in our intro physics classes. Let me know if you do anything that resembles this with your students. I'm going to give you a few just to practice this idea if you haven't used it lately. Okay, so I want you to draw a surface given this uniform electric field that's pointing to the right. I want you to draw a surface that would have positive flux, draw a surface that would have negative flux. Remember to label which way your dA is going. And draw a surface with zero flux. And there are many correct answers to all of these. So go ahead and give this a try. And unpause when you're ready to see my particular answers. Okay, so for my positive flux, I do a surface that's fully perpendicular to the electric field so that dA is totally parallel to the electric field, and I do dA pointing to the right. For the negative flux, I do the same thing, but the arrow is pointing to the left. Other correct answers would be a surface that rotated a little bit so that dA wasn't fully parallel to the electric field lines, but as long as it's not perpendicular, you can get either positive or negative. For my zero flux situation, I just drew a surface that was fully parallel to the electric field, which means that dA is perpendicular to the electric field. And I don't know about you, but I keep almost misspeaking because dA is perpendicular to the surface, so when the surface is parallel to the electric field lines, that means one thing, but when the dA vector is parallel to the electric field lines, that means something else. So you really need to be careful what you're saying. Okay. There are more answers that would give you zero flux. I'll be curious to know if any of you came up with anything else. Let me know in the problem solving discussion if you had any other ideas about zero flux. Now we're going to look at the electric flux through a couple other cases. This is really going to help us understand the physical meaning of Gauss's law and the divergence theorem and why it makes sense. So we're going to use the same electric field, and I have two questions for you. So this is a uniform electric field. It's the same everywhere in space. It's always pointing to the right with the same magnitude. What is the total flux through a cylinder? What about through a sphere? Okay, these are closed surfaces. All right, take a minute and think about that and unpause when you're ready to go. All right, let's think about what happens with the cylinder. Every field line that goes in here also comes out. So you have an arrow coming in on the left side, it's coming out on the right side. The top and bottom surfaces are parallel to the electric field lines, so those don't produce any flux. So you have surfaces that are parallel, so there's no flux, and then you have positive and negative flux canceling each other out. So the total flux through a cylinder is zero. We have the same thing happening in the sphere. For every arrow that goes in, there's an arrow that goes out. So we still get zero. All right, and this is the sort of thing you would see if you were, say you have a parallel plate capacitor and you're looking at the electric field between the two plates. Let's connect back to the charge distributions I had you draw earlier in the class. Okay, so going back to your drawings of the vector field you drew earlier, first think about your drawing of the vector field for positive and negative charges. I want you to look at that and think about what the flux would be on a sphere in various parts of that drawing. So what is the total flux through a sphere centered on the positive charge? What is the total flux through a sphere centered on the negative charge? What is the total flux through a sphere big enough to fit both charges? And what is the total flux through a sphere near the charges but containing neither? And I'm not looking for exact numerical answers. I want you to come up with an answer positive, negative, or zero. So remember, in a closed surface, a positive flux will be that the arrows are pointing out through the surface, and a negative flux when the arrows are pointing in towards the surface. And zero is when those vector field arrows are running parallel to the surface. Okay, go back to your drawing and think about what that should be. Okay, let's think through this. So I've gone ahead and sketched this a little bit bigger. So if we have a sphere centered on the positive charge, all of the arrows are going out perpendicularly through that surface. So because they're all going out, we have a positive flux. Now if our sphere is centered on the negative charge, all of our arrows are coming into the surface, so we have a negative flux. For the third one, let's say our sphere fits both charges. So if we imagine what our vector arrows look like over here we're primarily going to have arrows going out. Over here we're going to have a lot of arrows coming in. Over here we'll have a lot of arrows running parallel to the surface. Overall, the positive flux over here is going to balance out the negative flux over here. So we're going to get zero flux. Alright, now let's say we have a sphere that contains neither charge. Well, if that sphere was over here, you would see that every arrow that comes in has a corresponding arrow that comes out. That would give us zero. What if it was over here? Well, over here we'd have some big arrows going in and we have some small arrows going out. And overall that would balance out too. Even if you think about it right here. You're going to have more dense arrows coming in, but you're going to have a bigger surface area where they're coming out. So those things in the end will balance out as well. So that's zero. So what I want you to see from this is that if the surface contains a positive charge, you're going to have a positive flux. If the surface contains a negative charge, you're going to have a negative flux. If the surface does not contain a charge, it's going to be zero. Or if the surface contains positive and negative charges, but they balance each other out, you're going to have zero flux. That is what Gauss's law means, and you can see it from drawing pictures of it. And really, it's another way of understanding the divergence theorem. The divergence theorem says that the integral over the divergence equals the surface integral over your surface that encloses that volume. So just think about your positive and negative charges as your sources of positive and negative divergence, and you'll see that that matches up to your surface integral. Let me know if that makes sense. I really want to make sure you understand that conceptually before we do any calculations. Let's look at our example for the sheet of positive charge that you drew earlier. Okay, so looking at your drawing of the vector field around the sheet of positive charge, if you drew a box containing part of the sheet of the charge, what would the flux be? If you drew another box containing part of the sheet of charge, but it was a bigger box, what would the flux be? If you drew a box next to the sheet, but not containing it, what would the flux be? And again, I'm not looking for numbers, I'm just looking for positive, negative, or zero. Alright, pause and think about that. Okay, so I've drawn a bigger version of my sheet of positive charge. I just drew a bunch of plus signs. That's my sheet of positive charge. So all my arrows are going out. So if I draw a box that's containing part of this sheet, well, on this side the arrows are going to the left, on this side the arrows are going to the right, but remember DA is pointing to the right on the right, and DA is pointing to the left on the left. All of these arrows are going out. So for the first question, we have positive flux. If the box was bigger, but you can make it longer, you're still going to have positive flux. You can make it wider, still going to have positive flux. Now what if your box is out here and doesn't contain any charges? Well, for every arrow that comes in, there'll be another arrow that goes out. So that'll be 0. So again, you see that the flux is related to what charge is inside your box. So as long as the box contains some of those positive charges, you'll have positive flux. If your box doesn't contain any of the positive charges, the arrows in are going to balance the arrows out, and you'll get 0 flux. Now before you do this, we don't know how the electric field changes as you get further away from the sheet of charge. But we can use Gauss's law to figure that out. And I hope you're starting to think about, well, wait a minute, if the arrows in have to bounce the arrows out in this geometry, what does that tell us about the electric field and how it varies as you move away from this sheet of charge? And I hope you're starting to think about that. But we'll do this mathematically next week, so you can check if your understanding is working out. So really what I want you to have gotten out of class today is thinking about how every charge is a source of divergence and how that leads to a surface containing those charges having flux. So positive charges lead to positive divergence and positive flux. Negative charges have negative divergence and give you negative flux for that surface enclosing it. If your surface contains no charges, the geometry is going to work out so that your electric flux is 0 and your total divergence is 0. Alright, we'll actually do some calculations with this next week, but a lot of you were saying you were having trouble with thinking about your vector fields, and I hope connecting it to something with the real physical reality has helped you out with that. Let me know if you have any questions or feedback for me in the problem solving discussions, and please do talk to each other in those discussions.